our fourth. So today we'll be going through our fourth unit, that is graph searching and traversal. So graph searching and traversal tree, then you're going to know always there are two types of nodes within that, root node and the leaf node. Then what are the different kinds of graphs? So we have already gone through this. One is the undirected graph, wherein you don't find any direction being mentioned on a given graph in the path or on the edge. You're going to call it as a undirected graph. Directed graph always specifies the direction in which its path is being mentioned. Then weighted graph. Weighted graph is the path is being given certain number. That number itself depicts the weight of that particular edge and it is called as a weighted graph. Then a cyclic graph. What does that mean? So always a cyclic graph will start from one vertex and again comes and ends at the same vertex. So always it keeps cycling across the same vertex. And already I've explained. So then where are the applications of these graphs? So these graphs are basically used in your social networks, such as your Facebooks. You would have already seen there, so you may be knowing, you may come up with the suggestions there. So how do you think these suggestions are coming up? So suggestion for your friend request, you can see there they're coming up. So how is this happening there? So somebody who is your friend would be the friend for the person whom you're getting as a suggestion. So basically looking at that, you may be getting it as a suggestion. And the other thing would be you would have fed certain data, say your phone number, and you're using your Facebook application on it. Then what happens? Again, you get the suggestion there. Suppose if that person whose number you have fed into your phone as not your friend on your Facebook, you still get the suggestions. So you can just have a look at it. The same thing happens even with the Instagram and Facebook as well. And suppose if you have certain information that you are from a particular college, you may get the information of those students who study in the same college or those persons who have mentioned the same college. You may get some of them as the suggestions. So this is how you can see the applications of it. Any social networking, you can see there you get this, there is the usage of these graphs. Maybe if you are looking out for people who are interested in similar kind of hobbies or something like that, then always you come up with the applications of these graphs, wherein they try matching up which are those people who are with the same interests. So now we shall understand how these graphs can be represented. So one kind of representation of this graph is an adjacency matrix, which you have already learned in case of all your algorithms, mostly with the washes and flights. We basically solve them using these adjacency matrix. So what is this? There lots of space complexity because you have to represent zeros as well. One what you looked at as a undirected graph, and this is a directed graph. In this case, again, how you're going to represent, the representation still remains the same. From 1, if you're starting, you're looking for those two edges which are adjacent to it, from 1 to 2 and from 1 to 4. So you're representing it here as from 1 to 2 and from 2 to 4. Similarly, when you go for 2, so what are the edges that are going out from 2? So it has only one adjacent edge, that is a 5. So you're going to represent it as 5. When you go with 3, it has how many edges there? It has 3 edges and then one is looping. So it is looping for 6 itself. So you're going to retain it as it is. So one edge from 1 to 5, the other one is from 6, since it is a looping one, self loop. So you're going to retain it as 6 itself. Now, when you go for 2, when you go for 4, you have only one edge which is coming out of 4, that is 2. That is reaching 2. So you're going to mark it as 2 here. And when you go for 5, you have only one edge that's going out from here, that is from 5 to that's from 5 to 4. And similarly, You have from 6. So 6, it is self looped, so you're going to just represent it as 6 from 6 to 6 because it's a self loop. It has one edge which is going from 6 to 6 itself. So you're going to mark it as 6 itself there. So similarly, you can look for the other example as well. So next is what are these graph traversals? So how are those graph traversals? So graph traversals, I guess you have already learned it in your DS. So that is basically how is traversal is nothing but how do you traverse any given graph, and in this you have two. One is breadth first search and the other one is depth first search. So always when you are going for these traversals, you come across two terminologies. One is visiting a vertex and other one is exploring a vertex. So when you go with the so let us consider this as a tree, and I'll just brief out what do you mean by actually BFS and what do you mean by DFS. So let's first go with BFS. BFS is nothing but breadth first search. So how you're going to search? You're going to search it in the breadth because the name itself suggests you. So look at this, consider this tree. So now when I want to apply the breadth first search for this tree, so I will start my traversal from this. So first I visit this node 1, which is my root node. So from this, next what I have to see, once I visit this node, then I will start exploration of this vertex or this node. So what is the exploration? It has two. It has two edges which are going out from this. One is 2 and the other one is 3. So I can either choose 3 from 1 to 3. I can go and visit from 1 to 3, or I can visit from 1 to 2 first, anything. So first what I will do, from 1 I will go visit 2, since it's a breadth first search. Then again I will visit 3. So from 1 I went to 2, from 2 I went to 3. Now once I am done with this, I have looked into all the vertices which are at my level 1. So if it is level 0, this is level 1. So I have looked in all the vertices that are at level 1. So next I have to go through is my level 3. So when I have to go to my level 3, what I have to do here? Now again, see, I have 4 different vertices. I can still choose anything from, but I'm going to choose it from 2 now. So from 2 I'm going to explore to 4, from there to 5, then to 6, then to 7. So what does this say? I'm going to order them based on my level because it is breadth first search. So I have mentioned it as a level order, wherein so you just check. So first I started from my level 0 and I completed all the vertices at level 1. Then I completed all the vertices at level 3. So this is how you can go through for breadth first search. Next is depth first search. So depth first search is what? I start my I start my searching from the first vertex, that is from 1. So from 1 I will go to 2. So once I reach 2, see here from 1 I have an option, either I can go and visit 2 or I can go and visit 3. So I have two options here. So what I will do, I will go and visit my vertex 2. So when I visit this vertex 2, what is the option? What is the next option I have? So since it is a depth first search, I have to check which are the other vertices that are connected for this. So which are the other vertices that are connected for 2 now? 4 and 5. So once I visit this, I have to explore next vertex. So what is it? The next vertex which I am going to explore is 4. So once I have done with 4, I don't have 4 connected to any other vertices. So what happens now? I have to return back to 2. So once I return back to 2, is there any other vertex which is connected to 2? and I have not visited it. Yes. So 5 is the vertex which is connected to 2 and I haven't visited it. So what I will do here, I'll go to 5. I'll look at 5 and I'll visit this 5. So after 4 I'm going to visit 5. So once I finish with 5, there is no other vertex connected to 5. So what I'll do, I will come back and at 2 again I'll check if there is any other vertex which is being connected from 2. No, there is no other vertex that is being connected from 2. So what I will do, I will move back one more step, that is for 1. So once I reach 1, see from 1 I had two vertices that were connected, which was that one was 2 and the other one was 3. So exploring my second vertex I already completed, but I'm still left out with exploring my third vertex. So now I'll reach this vertex 3. So once I reach this vertex 3, now again I will check, is there any other vertex which is connected with 3? Yes, I do have two vertices, that is 6 and 7, which are connected to 3. So now what I will do, I'll go visit this vertex 6 and check if there are any other vertices that are being connected to 6. No, I don't find any vertex which are being connected to 6. So what I'll do, I'll come back to this one, that is vertex 3, and check if there is any other vertex which I have connected to 3 and I haven't visited. Yes, there is the vertex 7 which is connected to this and I haven't visited it. So what I will do here, I'll come to 7 and again try exploring it, but I don't find any other vertices that are being connected to this. So what I will do there, I will again go back to 3 and check for any other vertices that are connected to 3. Yes, I don't have any other vertices that are connected to this 3. So what I will do? Again I will go back to 1. Do you find any other vertex that is being connected to 1 and which you have not visited here? No, you don't have any other vertex. So what? So now you have completed your depth first search. So what you're going to do there, you're going to traverse it from 1 to till the end of it, and each time you have to remember what, if you are visiting one vertex, you should start exploring the next vertex. You're not going to do it at the level, so you can also call it as a pre-order. So these are two different ways how you can search for any given graph. So this basic understanding of breadth first search and depth first search is enough. Next what we will be going through is, so I've explained you this one because you require them to go through the next algorithm what we will be learning. So you have various algorithms which are based on this breadth first search and depth first search. So before going to this algorithm, we have to understand certain things, such as what are these connected components for any given graph. So uh, So connected components for any given graph here is, suppose let me take G as a set of graphs. So G is a set of graph and it has how many components within this? It has three different components which are within this. So now see, and there is no connectivity between these components what we find here. So such kinds of components within a graph which have no connectivity with each other are called as connected components. So you can look here. So you have how many vertices here? I have 5 vertices and these 5 vertices are connected like this, and I have the second component which has again how many vertices? 5 vertices, and these 5 vertices are connected like this, and the third component again 5 vertices and these 5 vertices are connected in this way, and there is no any other connection that is there between these different vertices. So such kinds of graphs you are going to call them as connected components. Similarly, you can just have a look at this. See, it has how many vertex there? It has two vertex for any given graph set G. It has only one vertex. Even these two are called the connected components because there is only one vertex and there is no other edge going from this. So this individually stands as a different component, and there are two vertices and there is one edge going between these two. So this whole individually stands as a second component. So this is how you are going to say them as two different connected components. So next what we have to understand is the strongly connected component. So strongly connected component is what? So for any given directed graph, you're going to say this graph has a strongly connected component within that only when you have directed graph is a maximally strongly connected graph. So whenever it has maximally strongly connected graph, so what do you mean by maximally strongly connected graph? You try how many number of maximum edges can together form this particular component. So these are standing as the connected components individually, but you say them as strongly connected only when you have one path that is connecting each of these components separately. So look at this. This is also only one path that is being connected, this one. So now in this, if you are supposed to identify which are strongly connected edges, you can see there from 1 to 0 I have a connection, from 0 to 2 again, from 2 to 1. So all these together they are forming one strongly connected component. And similarly from 3, so from 3 to 0 itself you have a direction, nothing other than that. From 3 to 4 again you form a direction, but individually this doesn't have any other components that can be connected for this. So for this any given graph you are going to say that, see, if I am going for 4, I don't have any other wedge going from 4, but I have only the edge that is going from 3 to 4, but there is no edge that is going from 4 to anywhere. So this stands individually as a vertex wherein it doesn't go anywhere. Similarly, this 3 also stands individually. So such kinds of components you're going to call them as strongly connected components. So to determine for any given graph which are the strongly connected connected components is our next task. So to do that you will be going across a algorithm called as Kosaraju's algorithm. So I'll be explaining that, but before we go with it, for identifying any strongly connected component, it is always dependent on the vertex and the edges that are present there, because you have to keep traversing all the vertices and the edges which are given in a what one by one pop the vertex from S while S is not empty. Let the popped vertex be V. Take as source and do the DFS call on V. So what you have to do now, you have to pop the first element from this stack. Which is the first element? 7. So what I will do now, I will start applying DFS from 7. So when I go with 7, what is the adjacent edge which is going out from 7? Do I have any adjacent edges? So there are no adjacent edges which are present or which are to be visited from 7. So I conclude my visiting at 7 here and send this one as the strongly connected component, because there are no other edges to be visited from this 7. So 7 is the individual strongly connected component. Next, so I have popped this. So the next element in the stack is what? 8. Now I go and visit 8. So the vertex when I visit 8 is what? It is 3. Then from this, which is the adjacent vertex there? So I have only one adjacent vertex, that is 7, but 7 is already being visited. So I'm going to end up this at 4 itself. So do I have any other adjacent edges which are to be visited? There is no other edges. So I conclude what? The second strongly connected component is what? 8. Now I go once again here. Look at what is the next element present there in the stack. It is 0. So at 5 I visit 0. So from 0 I have next next adjacent edge, that is 3. So I go to 3 here at 6. So once I go to 3 here at 6, I will mark this 6. So once I go and visit this, what is the next adjacent edge that is being connected from 3? So the next adjacent edge that is connected to 3 is 2. So at 7 I will visit 2. From 2, what is the next adjacent edge that is being connected? It is 1. So I am going to visit this one at 8. So I am going to visit this one at 8 now. Now from this you have one more adjacent edge which is present, but then look at this. We have visited this 5. We have visited this 5. So what we visited this at 5. So what I'm going to do, I'm going to say that I have no other adjacent edges to be visited and finish visiting one here. So now at this as a whole, see, you started it from 0 and you finished your visiting at 1. So 0, 3, 2, 1. These form a strongly connected components. So this is your third strongly connected component. And then now which are all the elements you have popped out? See, 0 is popped, 1 is popped, 2 is popped, and what is next left out? So 4 is next left out. Now again apply DFS from 4. So once you so so sorry, once you finish at 9, you visit back again. This is 10. You visit back again at 11. You visit back here at 12. So completely you finish visiting all these components and you update them as 0, 3, 2, 1. Now what is left out? So you have popped all these elements whichever you have finished visiting. Now at the stack at top you can see what? 4. So now again I'll start visiting from 4. So 4 you have visited at 13. From 4 you go to 14. From 14 you go to 15, that is 5. And from 5 you find only one adjacent edge, that is for 4, but you need not visit it because you have already finished visiting it. So you stop visiting your 5 at this point, move back, and this is 6. So from 6 also you stop visiting it because you already have visited the 7 and you have already visited 5. So you're going to conclude this and you're going to pop out. Similarly, from this you're going to go for 4 and you're going to pop out. So what you did continuously, you visited all this and you finished visiting it. So your next connected component is what? 4, 5, 6, and all the elements are now popped out of the stack. So you stop your algorithm here. That is, once you pop out all the elements from the stack, you stop it and check which are the strongly connected components. So each time you finish visiting a set of vertices, you are going to update them as your strongly connected components. So this is how your Kosaraju. So first is equal to one endpoint of the E and second is equal to other endpoint. So what you are going to do here, since you reverse it, you are going to store it in the adjacent. So this is how you are going to do it for any given graph. So this is how you're going to apply Kosaraju's algorithm. And the analysis here is what? The time complexity of this is given in the form of vertex plus the edges, where V is the number of vertices and E is the edges, and here DFS is applied twice on the given graph. So as long as you find as long as you find the vertex being visited, you keep applying the DFS here on the given graph. So once you apply it, you have to do it by yourself and always have, see here, you, that's what formally it is being defined as GV of B a graph. A subgraph is called matching M of G if each vertex of G is incident with at most one edge in M. So at least it has to have one edge in M, and the degree of V should be less than or equal to 1. It says that the degree of V should be less than or equal to 1. So in this, see here, it has been given there, it has only one edge, that is from A to B, and C and D are just the vertices as it is. Still it is okay, because what is this? It has only one edge. And the other definition says that for any given vertex, either it can have zero edge or one edge. Since all these vertices, so none of these vertices are connected, they are all having the degree as 0. So the degree of any vertex is how many number of edges are being drawn from that particular vertex. So in this vertices, you can see that there are no any vertices that are being drawn, there are no any edges that are being drawn from these vertices. So all these are the different matchings for this given graph. So next what you have to understand is what is maximum matching. So maximum matching is the number of edges in the maximum matching graph is called the its matching number. So what is this? So here when you are given this, you have to check, see how many maximum matching you can form. So suppose if I am going to have this with the five edges like this, so the maximum matching edges could be what? Matching graphs which can have maximum edges is what? 2. So these are the maximum matching. So maximum matching here says the number of edges. That's what. The number of edges in maximum matching graph is called matching number. Because see, it has how many edges here? One is from C to D or from A to B. The other one would be what? From A to C or from D to B. Only these two could be the maximum match of this graph matching. So next part what we'll be going through is the flow networks. So as I told, these flow networks are again based on this maximum matching of the graphs, or I can say that graph matching. So in these flow networks, it is always indicated as in any real time. So the flow of networks can be considered same like your flow of liquids through the pipes or flow of the current through wires. Delivery of any goods can be modeled using these flow of networks. So what is this modeling of this flow of networks says you? So basically you can keep track of on your online buying websites, you can keep track of your order, right? What you're going to see there. So it gives you the information like how it is being shipped now currently, where is your order, and when actually it can reach you. So what is that? You can see there it actually routes you through the graph there. So this could be an example how actually the flow of that. So there could be a best path which can be chosen based on this flow. So now let's formally go through this. Flow network is a directed graph which has a set of vertices and edges, and for each vertex, each edge you can say it as u comma v will belong to E, and we associate a non-negative weight capacity, and there is a capacity that is being defined for each of these edge. So what is that capacity? It should be either greater than or equal to 0. So it cannot be a negative. And we assume that C of UV is a graph, in any of the given flow graph, it is always with the sink and the source. So there exists a sink, there exists a source and the sink. Source is the place from where you are going to start or originate, and sink is a place where you are going to conclude, or you can also say it as the destination. So uh, always it says that the flow of this network should follow the following condition. So what is that? For any non-source and a non-sink node, the input flow is equal to the output flow. So I'll be just showing you with an example that would help you understand these conditions better there. So we'll go with that. And next, so what kind of problem are we going to address here? So it is the maximum flow. So the maximum flow is what? So it says non-empty backward edges. You can see here, each time when you go, you can see there the capacity of it is either incremented by 1, and that value is again dependent on the minimal cut. So this is again dependent